So in this video we're going to be taking a look at the modulus function. So picture it that we have a number line and 0 is here in the middle. To the right of 0 we're going to have positive values, and to the left of 0 we're going to have our negative values. So if we are asked to find the modulus of 10, we want to find the absolute value. So the distance that we must travel from 0 in order to reach 10. Well, to reach 10 we need to go 10 units. So the modulus of 10 is simply 10. If we have to go and find the modulus of 30, what that means is it's asking us how many units must we go from 0 in order to reach 30. That's simply 30 units. Now what if it's a negative value? What if it's negative 5, the modulus of negative 5? So picture this, we have negative 5 here. How many units must we go from 0 to get to negative 5? Well, we must travel 5 units, so it's going to be 5. What about if it's negative 100? So the modulus of negative 100. To get from 0 to negative 100, how many units do we have to travel? We have to go 100 units. And from these examples, we can see that there's a pattern forming where the output of any modulus is always going to be a positive value, no matter what that value inside the modulus function is, right? Whether it's negative, whether it's positive, it's still going to output a positive value. And we can use this when we are asked to graph modulus functions. So let's say we have to graph the modulus of x minus 3. So we have to quickly draw our x and y axes. Right, so here is our y, here is our x. We'll put in 1, 2, 3, 4, 5. Right, so this is what can come up in the test. You're going to have to be able to draw your own axes. So a way I remember it is y to the sky. So y is always going up, and that's how I like to remember which one is the y and which one is the x axis. 4, and then here we'll have negative 1, negative 2, and here we'll have negative 1 and negative 2. So to graph the modulus function of x minus 3, well, to find the first point, what we can go ahead and do is substitute in y is equal to 0, right? So if 0 is equal to x minus 3, then x must be equal to positive 3. Okay, so we're going to have one point here. That's going to be our very first point. Now, the next thing that we can do is on our calculator, what we have is we have a button that says ABS. That means absolute value. And that is what we use when we have modulus function questions. So let's go ahead and plug in a value 4. Okay, let's say it's 4, x is equal to 4 minus 3. So the modulus of 4 minus 3, y is equal to 1. So we're going to have, if we go up here, so it's going to be somewhere here. That's going to be our first point. If we put in x is equal to 5, so we're going to go here, x is equal to 5, we get that y is equal to 2. So here's going to be our 2 value, about there is going to be our 5. So we're going to have something like that. Now, what we would normally have if we were to draw a linear graph, a linear equation, we just have a straight line, whether it be that way or this way, or anyway, it would just be a straight line. Now what's interesting and what's different and what's unique actually about the modulus function is that instead of continuing and being a straight line, we actually end up getting a V shape. And that's because, going back to this idea that the output is always positive, that means, so it's either 0 or positive, greater than or equal to 0, we're never going to go beneath y is equal to 0. We're never going to go down this way. It's always going to be above. We're always going to have an output that's a positive value, and that means that y is always going to be positive. So here, when we go ahead and we substitute x is equal to 2, we're going to get 1. So we're going to have, it's a reflection from this vertex, from that vertex of 3, if x is equal to 3. Now, if we go to 1, we have y is equal to 2. And so what we end up getting is this V-shaped graph, right, with a vertex at x is equal to 3. Now, what about if we are asked to draw the graph of the modulus function x plus, let's say, 2b? Okay, it's an unknown constant. Well, what we can do, again, we have to draw out our x and y axes. Okay, so our y and our x. We have to put in some values, 1, 2, 3. Here we'll have -1, -2, -3, and -4. Right, in the test, make sure you use a ruler for all of your lines. You'll have 1, 2, 3. Here 1, 2, so -1, -2. So, what did we do before? Well, we set y is equal to 0, so let's go ahead and do that. So 0 is equal to x plus 2b, so x is equal to -2b. Now, I made a slight error here because we have an unknown constant. So in fact, we're not actually going to have, it's not going to be -1, -2, -3, -4, whatever. It's going to be -2b. So that's the main point that we need to mark. So it's -2b. Now, what we can see is that the gradient is 1. There's no leading coefficient. So what we're going to do is we're going to be able to go across 1 unit, up 1 unit, across 1 unit, up 1 unit. Now, using the information that we found in this other question, we can see it's a V shape with the vertex at that point. So on the to the left of that point, it's going to be the same idea: across 1, up 1, across 1, up 1. And so then what we're going to end up getting is a modulus graph with a vertex at -2b. And that's the answer. Now, the final point that I want to cover is in the situation where we have, let's say, an equation that involves modulus functions. So let's say, for example, we have the modulus of x plus 2 is equal to the modulus of x minus 4. And they want us to find where the x value which makes this true. Now, the first way that we can do this is we could try and graph them. Do a graph, do a drawing of both of these modulus functions, and then find the point of intersection. And that's what we're going to do here. For the first method, we're going to graph them both. So 1, 2, 3, 4. Remember, y to the sky, and x is the other axes. Okay, and then -1 here. Okay, so the first thing we're going to do, let's go ahead and graph this modulus function. So it's going to be 0 is equal to x plus 2. So x must be equal to -2. So we're going to have our vertex here at -2. We see the coefficient of x is 1. So it's going to be a basic across 1, up 1 graph. Across 1, up 1. Across 1, up 1. And the same here again. Across 1, up 1. Across 1, up about here, up 1. And then we can go ahead and draw these lines. So we'll have a modulus graph that looks something like that. Oops, I slightly drew beneath the x-axis. And now for this graph here, 0 is equal to x minus 4. So our vertex will be at x is equal to 4. Okay, so we're going to have something here. I'll just draw a couple more. 1, 2, 3, 4, 5, 6. Okay, again, the coefficient is 1, so it's just going to be across 1, up 1. Across 1, up 1. Across 1, up 1. And then the same goes here, across 1, and then we'll go up 1 to about there. And what we end up getting is two modulus function graphs that intersect at a point. Here, right, we can see that. Now, it looks to me as though that's going to be 1. So I think that x is going to be equal to 1. But the way that we can be sure is we can go ahead and solve it algebraically. Now, the way we do this is we want to try and remove the modulus signs. And the way we can do that, okay, if this modulus function, for example, was equal to -5, let's just say a random value. If we were to square it, we would be removing the modulus signs. And then what we would be left with is just a positive value, which we can then go ahead and solve. So what we try and do in these situations is we square everything. We square the modulus functions. And then what we're going to be left with is just x plus 2 squared is equal to x minus 4 squared. And then we expand these and then we can solve for x. So we'll do that. So x squared, we're going to have plus 4x plus 4 is equal to x squared minus 8x plus 16. Bring everything to the left side, so x squared minus x squared is 0x squared. 4x plus 8x is going to be 12x. And then we're going to bring the 16 over, so that's going to be 4 minus 16 is negative 12 is equal to 0. Now we solve for x, so 12x is equal to 12. Divide both sides by 12. X is simply equal to 1. So we saw it in the graph when we graphed them, but this is how we do it algebraically. And then let's go ahead and check that. So if we have to substitute in 1 as the x value, so on the left side we're going to get 3, and then on the right side 1 minus 4 is also equal to 3 when we use the modulus. So that is how we solve that question. Now the key ideas, looking over this entire video, is just to make sure that we understand that the modulus function always will output a positive value. And because of that, when we want to graph modulus functions, we're always going to have a graph that remains at y is equal to 0 or greater than 0, right? So y is equal to or greater than 0. And because of that, because y never is negative, what we're going to end up having is a v-shaped graph if it's a linear equation. If it's to be a quadratic, like x squared or something, then it's going to look somewhat like this, right? But it will still, where this here is the x-axis. Okay, so that's important there. And then here, when we have to solve an equation which involves modulus functions, what we do is we square both functions, both sides, in order to remove the modulus signs and be able to actually solve the equation and find the value of x for where the two intersect. And that's it for this video.